Hi, my name is Tiagi, and in this video, I'll be going over lines, planes, and points, and their notation, how to calculate the angles between them, distances, and intersection in 3D. So to start, let's go over how to define lines, planes, and points in 3D. So the first way to define is a point, and a point's pretty simple to define, right? So in 2D, we define a point as xy. 3D, we define it as xyz, where x corresponds to how far on the x-axis, y corresponds to the y-axis, z corresponds to the z-axis. So we have a point like so with x, y, z. Next, we have a line. So in 2D, when we want to find a line, we had a slope and we had a y-intercept, or kind of a point, on that line. In 3D, it's kind of the same thing. We have a point plus a vector, and the vector kind of jumps in for the slope. And so here's a way to visualize it. If we have a vector v, right, this is called a direction vector, and it tells us what direction our line's going in. If we have a vector v, we need a point called p, and then from that, we know the vector v is in this direction, so we can define a line L in that direction. And so to define a line, we need a point and a vector, and the idea is the vector is going to have what's called ABC, the vector, and let's call the point x0, y0, and z0. So two ways we can define a line in 3D is through this thing called parametric form, which is x equals x0 plus at, y equals y0 plus bt, and z equals z0 plus ct. And this is called parametric form. We can also define it in terms of symmetric form. And basically, the way to define symmetric form is we solve each of these equations for t, and we set them equal to each other. So we solve x, this first one, we subtract x0, we get x minus x0, divided by a, we get the x minus x0 divided by a is equal to t. Same thing with other equations, we get that y minus y0 is equal to b, and z minus z0 divided by c is equal all to each other. So most of the time, the parametric form is going to be more useful, but these are two ways you can express a line in 3D. So some general things to know about lines. One, if a line has its vector, its direction vector, a, b, or c, one of the components, equal to 0, then we say that line lies on the plane that is 0 for it. So for example, if we say a equals 0, then looking at our equation, what we're going to get is that x equals x0, and therefore this line lies on the plane x equals x0, and it's parallel to the yz plane. And the reason why is because if you see this our x-axis, right, if we have just a line on that axis, just like straight down, right, it's going to be parallel to the yz axis because it's intersecting the x. So x equals x0 means it's parallel to yz plane. Okay. 2, if the direction vectors are parallel, then the line is parallel, and consequently, if the direction vectors are perpendicular and the line intersects, then the lines are perpendicular. And number 3, lines in 3D can either intersect, they can be skew, or they can just be parallel. So while in 2D we only have two options, intersect or parallel, in 3D we have another option called skew. The reason why is because in 3D the lines can just go like on top of each other and they don't have to be parallel, and they can just never touch if they go like kind of on top of each other. So we have that option. Next, how to define a plane in 3D. In 3D, to define a plane, we need a point and we need a vector, but this vector is a normal vector. So a normal vector is a vector perpendicular to the plane. So for example, if we have a plane, right, the normal vector is going to be the vector that's perpendicular to that plane. And so the idea is if we have a point on this plane and we create a vector from that plane, so point 0, right, same thing there, it's a point p vector times, and if we take the dot product of those, we're going to get 0, because if we have a dot product and they're both orthogonal or perpendicular, we get 0. And so using this fact, what people have made is an equation that states a times x minus x0, sorry, I'm just going to do that, b times y minus y0 plus c times z minus z0 is equal to 0. And this is called the standard form equation. So again, ABC is just a normal vector, its components, and then x0, y0, and z0 is just the point P that we picked. So it's pretty similar to kind of this equation, but again, it's a little different because we're using normal vector instead of direction vector. Next, if we take this equation and we expand it, what we get is ax minus ax0 plus by, by0, and c0. Those are all constants, right? And so we can take these constants and put them all in another constant called d and move it to the right side. If we do that, we get that ax plus by plus cz is equal to d. And this is called the general form for a plane equation. And the main thing to know here is that if the normal vectors are perpendicular or parallel, then the planes are perpendicular or parallel. And another thing is in 3D, planes can only either intersect or be parallel. So similar to lines in 2D, they cannot be skew because if you imagine a plane goes on infinitely, so it really has only two options: to be parallel or intersect at some point on that infinite coordinate system. So that's definitions and notation. Next, we'll go into some actual kind of math with them. So first, how do we find the intersection between these different 3D objects? So to start, how do we find the intersection between a plane and a plane? So let me just draw a diagram quickly. So if we have a plane, right, like here, if we have a plane like here, the first thing we can see is that their intersection is a line, which makes sense, right? Because the plane is going to be intersecting at an infinite amount of points because it has, width. And so we can see that it makes a line, and we have this. So the first step in finding out well, first of all, whenever we do an intersection, the first thing we need to check is if the objects are parallel. And this is a pretty easy check, right? We just use scalar multiples. So if they're scalar multiples of each other, the vectors, direction or normal vectors, then they're going to be parallel. And the reason we want to check for this is if it's parallel, then it's not going to intersect. So that's why we always check that for first when we're solving the intersection problems. Next, so if we have these two planes, first things first is we take the normal vectors of the planes. So call this normal 1, call this normal 2. So we take these normal vectors, and if you see, if we take the cross product and get a perpendicular vector to these normal vectors, right, we're going to get a vector, right, it's cross product. So we take the cross product, we'll get a vector called v that is parallel to the line L. So that's useful because remember, to define a line, we need a vector and we need a point. So by doing the cross product of the normal vectors, we get a parallel vector that is the direction vector for the line. So the first step when you're doing this is to take the cross product of the normals. So just to write that out, normal 1 cross product normal 2 gives us our vector v. So we have our vector v. Second step is to find a point P on that line. And the way we find that point P on that line is we said either x or y or z equal to 0, and then we just solve using the two equations that are formed for the point P. So we use that and we solve for the point P. And once we have the vector v and we have the point, we can make the equation for the line just by combining the vector v and the point P. So plane is not too bad. How do we find the intersection between a plane and a line? So for a plane and a line, the first thing you have to check is if you want to check if it's parallel, right? You have to check for the dot product equaling 0. And the reason why is because if the dot product equals 0, so let's imagine that we have a line and a plane, right? The plane is going to be perpendicular, right? It's going to give a vector that's perpendicular. Well, the direction vector is going to be parallel to the line. And so if the two are parallel to each other, then the cross product, since it's a normal vector, should be 0 because the dot product should be 0 because the dot product of two perpendicular or orthogonal vectors is equal to 0. Okay? So first check that. Then, so let's say the equation of the line is x equals x0 plus at, y equals y0 plus bt, and z equals z0 plus ct, right? And so we have the plane equation, ax plus by plus cz equals d. So you'll notice if we take all these equations and plug them in, so we take x equals this and plug it into here, y equals this, plug it into there, z equals this, and plug it into there, what we get is we have one equation with just one unknown, and the unknown is t. That's our parameter. And again, the reason why is because x here is a constant, a is a constant, a is here a constant, d is a constant. So the only unknown when we plug all these in is t. And so because of that, we have one equation, one unknown. We can solve for t. Okay, so now that we have t, what we have to do is we have to find our intersection points. We just find x, y, z from our t value, and we've solved the intersection between a plane and a line. Pretty simple. Next we'll go over line and line. So if we want to find the intersection point between a line and a line, right, there's three options. They're either parallel, so if they're parallel, they can't intersect, but there's also the option that they skew. So how do we deal with that? So the first step is, let's say we have two equations. Again, x equals x0 plus at, called t1 because we have two equations, right? Y equals y0 plus bt1, and z equals z0 plus ct1. Same thing over here, except now I'm going to use t2. Okay, so the idea here is we set x is x. We can set them equal to each other. So we can set x0 for the first equation plus at1 equal to x0 the second equation plus at2. If we can do this for all the equations, you'll see that, again, x0 and a are both constants, same with all other ones. The only variables we have are t1 and t2, and we have three equations. So what you do is you take two equations and you solve for t1 and t2 using those two equations. Then, once you have solved for those two parameters, you plug in t1 and t2 back into the third equation. Okay, and the idea here is if that third equation, when you plug it back in, doesn't equal each other, right? If this doesn't equal this, then you know that, okay, this solution does not work, and therefore the lines are askew. So again, lines are askew if you solve for t1 and t2 and you plug it back in and they're not equal to each other. But let's say they are equal to each other. Well, if they're equal to each other, you have t, so all you have to do now is find the point, x, y, z, where they intersect. And to find the point, again, it's pretty simple, I think. You just plug in t1 or t2 into your equations and find the point where they intersect. And that's how you find an intersection between 3D objects. Next, let's go into the angle. How do you find the angle between objects in 3D? So for lines and planes, I think they're pretty obvious. So for planes, plus planes, slash lines plus lines, to find the angle, right? So we know the dot product gives us cosine theta. We can exploit that fact into finding the angle between these things. And so the idea is we take whatever vector we're given, so either direction or the normal vector, and we use the formula, right? So we know that the dot product, so let's say we have vector 1, vector 2, we have two lines, right? We know the fact that the magnitude of the vectors times cosine theta is equal to the dot product. So therefore, cosine, the inverse cosine of the vectors dotted divided by their magnitudes multiplied equals theta. And this works again for normal vectors too, because normal vectors can tell us the perpendicularity between two planes as well. And one thing to note is for lines, you also have to check if they intersect, right? Because if two lines are skewed, they're not going to have an angle between them because they don't intersect. So checking intersection for the lines is important as well. But how do we find the angle between a plane and a line that we know intersect? So let's draw a diagram. If we have a line, L, call this actually a plane P, and we have a line L, like so. If this plane P, right, we can extend a normal vector out. So we extend this normal vector out, and we have this line L, right? And again, we want to find the angle of beta here, so if that was not clear. Line L, right, has a vector V, direction vector, so we can start it from there, and normal vectors here. So as you can see, we have two vectors, and we have an angle between them. So we can find this angle using this property. It's the angle between these two vectors. Let's call it actually phi, right? So the angle between normal vector and this vector V for the line is equal to this, right? Normal times vector dotted divided by the magnitudes multiplied. And this equals phi. And so here we have a triangle, right? So this is also equal to phi because they're congruent angles. And so theta plus phi plus 90 equals 180, which means that theta is equal to 90 minus phi, and phi is this value. And so the way we solve for the angle is by using this formula, 90 minus cosine, inverse cosine of the dot product divided by the magnitudes of the normal vector of the plane and the direction vector of the line. So that's how we find the angle between two or these geometric objects in 3D. Finally, for the end, we'll go with distances. How do we find the distances between objects in 3D? First, how do we find a distance between two planes in 3D? So let's say we have two planes, right? Let me just draw them. And between these planes, we have a point P, random point, and point Q, another random point. And again, these two planes are parallel, because if they weren't parallel, you can imagine they'd intersect. And so their distances, their minimum distances, would be 0. And so it really doesn't matter for that. We're looking at parallel planes here. So again, we pick a point Q, pick a point P, and so if we draw a vector here, we have a normal vector going this way too, right? And the idea is we want to find length d of this vector. And so if this is a normal vector, right, extending out, and this is a PQ vector, you can see that all we're really doing is we're projecting this PQ vector onto the normal vector and seeing the distance. So basically we're finding the magnitude of the projection, so finding the magnitude of the projection of PQ on N. Okay, and so this magnitude is equal to, if we have two planes, AX plus BY plus CZ equals D1, and AX plus BY plus CZ equals D2, then we can say that the absolute value of D1 minus D2 over the magnitude of the normal vector, which we'll call ABC going forward. So ABC is equal divided by square root of A squared plus B squared over C squared, which is again the magnitude of AB of the normal vector. Okay, and an important thing to note with this is that if you use this equation, this one here, instead of this one, you have to make sure that your left-hand side of your planes are equal. And they should be equal. I mean, they might be scalar multiples, but they should be equal because they should be parallel if you're not trying to find a distance. But you want to make sure that they're the same in order to then plug into this equation here. Okay. All right, next. How do we find the distance between a plane and a point in 3D? So in a plane and a point, it's kind of similar to the last thing we just did. So plane and a point, if we have a plane, point, right? So we pick a random vector or point, P, call this Q. So the vector is going to look something like that. And then if we draw the normal vector, again, right? And like so, right? We're trying to project, again, the idea is we're projecting PQ onto N, and we're finding that distance, D, like so. So same thing, projection of PQ on N. In this case, the formula is that what we have, well, if we write the projection now, it's the dot product of N times PQ divided by the magnitude of N, right? And that is also equal to the absolute value of AX1 plus BY1 plus CZ1 minus D, where x1, y1, z1 are the points, q, the coordinates, and ABC is the normal vector components of the normal vector, and then d is just the value for the plane, divided by the magnitude of the normal vector, which is just square root of a squared plus b squared plus c squared. And again, the way we derive this is just a cross product, right? If you do the cross product between this, you'll get this answer for your cross product. And finally, plane plus line. So plane plus line is the exact same thing as a plane plus point. And the reason why is whenever using a plane plus line, the plane plus line have to be parallel to each other, because they're not parallel, they're going to intersect, and so the minimum distance is going to be 0. And so we don't want to solve a question where the minimum distance is 0. So if it's a plane and a line, they're going to be parallel, right? The plane and the line. And so again, the same process, we pick a random point Q, P, again, PQ, normal vector. You can see the same exact diagram here, except it's just a line. So it's the same exact process here. Really no change to the steps we did. Okay? Next, how do we find the distance between two skew lines? Okay? So for two skew lines, the first thing to know with two skew lines is that the lines are contained in parallel planes, which means we can create two planes that are parallel to each other that contain these lines, and then we can find distances from there. So the first step is to find the direction vectors. Then we cross those direction vectors to find the normal vector. And again, the reason why we cross those vectors to find normal vector is because we define a plane using a normal vector. So by crossing those two direction vectors, we're going to get the same normal vector. And because it's the same normal vector, we know that those two normal vectors are the same. And so therefore, their planes are parallel to each other because the normal vectors are the same. So we cross those, we find a normal vector, n, right? Then we also need to find 2 points, right? So find 2 points on each of the lines. I don't know, call it point P0 and P1, right? And once we have P0, P1, and normal vector, right, we create two equations of planes, right? Parallel planes. And at this point, since we have two equations of two parallel planes, we can just use the formula I wrote before to find the distance between those two planes. And that's kind of how we do skew lines. So really the process is we know that they're going to contain in parallel planes. We cross them to find normal vector, which then tells us that, okay, these are the normal vector for both the lines because they're parallel, and then we can find the distance of those two parallel planes. Finally, let's go over how to find the distance between a line and a point. So a line plus point. Quick diagram, let's say we have a line L, we have a point P, right, like so. We're going to do the same thing, we'll pick a point, random point P. Actually, call this Q instead of P. Point P, draw a vector, right? We have a kind of vector going here too from the line. This creates a triangle, right? And so this triangle, we know this angle here, theta, and we want to find this distance d. So we know the vector v here too as well. We know this vector v because we use the line, right? So we know the direction vector from a line. So because of this, we know this is v, we want to find this d, and we know this pq. So what we can do is we can say that, okay, well, d is equal to the magnitude of pq times sine theta, because sine theta is equal to opposite over hypotenuse. So magnitude of pq times sine theta is equal to d. And we realize, oh, pq sine theta, that kind of looks like the alternate definition for a cross product. So if we multiply it by v on both sides, we get that magnitude v, right? Magnitude v times pq times sine theta is equal to magnitude v times d. And this is actually the cross product between v and pq, the magnitude of it, right? And so now if we divide both sides by v, we'll get that the magnitude of the cross product of v, the direction vector for the line, times pq, where p is just a random point and q is the point, divided by the magnitude of v, gives us the distance between the line and the point. And that's the formula for finding the distance between a line and point. And again, another thing, trivial thing, is that parallel lines, right? Same thing process here, right? Because you can imagine if we have a parallel line, we have point P, random point Q, right? So it's the same kind of diagram, same exact process we did up here. And again, the reason why is because no matter what point we pick, since lines are parallel, the distance is constant. So we can pick any point and we'll get the correct answer no matter what we do. And finally, point plus point, that's kind of trivial, right? To find the distance between a point and a point, we just find the vector between them, vectorize it, and then we take the magnitude of that vector to find the distance. And yeah, that's lines, planes, points in 3D. Thank you all for watching, and I'll see you guys all tomorrow. Bye.